molecules. If you go by the origin of the so-called the linguistic, when you see throwback, right? So it's something related to what? Can you relate? Something related to color. Something related to color. So actually that was exactly happened more than 100 years. Those Russian scientists, they used technique. They happened to discover when they did the research, they used this technique. Then they discovered this technique is good for them to separate the pigments. You know pigments? For instance, chloroform, yes, from the leaf, from the plants. Leaf, why leaf is green? Because inside it contains chemicals, we call it pigments, right? Then they find a way to separate those color components. Then they discover this chromatography. So chromatography fundamentally is a separation technique. So it can separate chemical compounds, also called chemical molecules, in a product or in a sample by the distribution of the different molecules between two phases. One is called stationary phase. The other one is called mobile phase. And it's because when we apply this particular technique, right? When we use a gas as the mobile phase, all this data will elaborate. When we use gas as the mobile phase, then the entire technique, then after that, engineers, right, we kind of design different components and put them together and integrate it and then make it fully automatically operated. So this one we call it gas chromatography. If the mobile phase we use is a liquid, then we call it liquid chromatography. Simple as that. Alright. So may I ask any one of you had the experience, maybe even in your secondary school, did you kind of play around with like a tiny kind of a filter paper and then with a certain solvent and use that to separate things? That's called paper chromatography, right? That's somewhat very similar to a century ago, those Russian scientists when they first discovered this one. So that's called paper chromatography. It's the same principle. So in that case, the two phases, what are those two phases? We have a mobile phase. It's a solvent, right? It's an organic solvent we use. Then as the name suggests, mobile phase, the solvent. Can you recall what you observe when you play this little game, right? When you dip a tissue paper in that, then you can see something is on the move. What's the thing on the move? Solvent. Because it's on the move, so we call it mobile phase. Right? Then what is stationary phase?
The sample.
To be more precise, we are science students. More specific, more accurate. What is the other phase in that experiment? Paper chromatography. Actually, it's quite straightforward. The other phase is the filter paper. Can you recall when you play around with the experiment? So you take usually you prepare a long, very long paper, right? The fibers, all this you dig into a solvent, just one end, not 100%. You didn't throw in the entire thing. You just immerse the tip of the paper into that. Then you can see the solvents moving up. Then how about the paper? The paper is fixed there, right? Does paper moving around all the time? No, right? Once you hand it this way, so the paper is fixed there. In terms of position, in terms of angle, all this is fixed, right? So that's why literally we say the paper is the stationary phase for that. So it's a solid. It can be a liquid. So later on, based on this discovery, people further develop into the modern chromatography, right? But anyway, the very briefly, the principle is this technique is for compound separation. It helps to separate. It's quite effective to separate different kinds of organic molecules. And then the separation of these molecules in the sample is by the distribution of different molecules between these two phases. These two phases. One is for mobile phase. So then we look in more details. What are these two phases? So the next one, I'm going to introduce you. As discussed, so with this simple schematic diagram, probably it will help you a little bit more on how the so-called different molecules they are separated by using this technique. So the first graph, so from left to right, 1, 2, 3, 5, 5 different so-called the development phases. So first of all, let's say the vertical tube, you consider it as a column, we call it column. So when a mixture of the molecule, or so-called chemical compounds, they are introduced into this column, right? We call it, this column, we call it stationary phase, stationary phase. When it first introduced, it's a narrow band, right? It's a narrow band, it contains maybe multiple molecules, right? They are mixed together. So when the compounds move down the tube, the column, because the molecules then they will have interaction with the stationary phase. They will have the interaction with the molecule, because the interactions, the different molecules will have different interactions with the stationary phase. Then it results into the separation of the different molecules. So you can see that the band actually, when the whole thing moves down, the band gets broader. If the interaction of different molecules with the stationary phase, with the stationary phase is different enough, then what will happen is different molecules they are going to separate from each other, and very obviously, then you can observe that phase number 3 and number 4. If really the interaction between the molecule and then the stationary phase is really big enough, obvious enough, to an extent the color in different colors, right? For instance, blue color represent molecule 1, black color represent compound molecule number 2. They are fully separated. So that's what you can see from this so-called chromatography separation. So you can see this 5 actually means the so later on these separated molecules, they're going to come out from this column, okay, one by one. So that's why we can separate them, and later on, based on the separated molecule, we can identify them one by one. That's just a very brief introduction of this technique. Don't worry, we'll go into more details of the separation principle. Before we move into the separation principle again, so I'll show you the schematic of a modern gas chromatography instrumentation. So as discussed, for this separation, right, we need the column for compound separation. So there's a column here. Then we need the mobile phase, which is a gas. So that's why we need to provide the gas source. Usually gas are stored in a gas cylinder, the stainless steel gas cylinder. We use the pressure, use the so-called flow controller to control the speed of the gas, right? So gas coming in. Then we need a sample introduction system. This one we call it, in the instrumentation, we call it injector, sample injector. It's where we introduce the sample into the column for the separation to happen, right? And then this injector, right, usually what we do is, you try to visualize a medical injection syringe, right? Syringe with needle. So you put your sample into the syringe, then you inject through this injector. So it will go into this column. So GC column usually is a very tiny tube. I don't bring the actual sample column with me. Later I can show you a video clip, then you can have idea what is the actual column looks like. And probably later on, I can't recall for your class in the lab schedule. Later on when you go into lab, I'll be able to show you the actual one. So the very tiny tube columns, it can be very long. Sometimes we actually prepare the column in the length, usually 30 meters is very normal, or even 50 meters. So you can see a tube of 50 meters is how long. So that's why we roll it up. So it's a one row of the very tiny tubes. And because the tube is so tiny, we have another name to describe it. We call it capillary tube, capillary column, right? So that's a GC column. Then after that, so this end is for the compound, the mobile gas, and then your sample molecules come in. Then go through this column, go through and coming out. Then coming out, because we need to know when the molecules are coming out and who are they. So that's why we need a system to detect that. So that's why we need to design a detector which can detect the so-called the signal of the individual molecules. Right? So that's why we design this one. Later on we'll go into more detail. So that's why based on this principle, right, scientists develop different type of detectors. Right? But anyway, just very briefly touch on the overall. So you just need to remember there's a injector there, there's a detector there, there's a detector at the other end. So detect the individual molecules. But of course, nowadays the modern instrumentation, most of the operations can be operate automatically, right? So we need a computer system, right, to record the data, to record the electronic signal, then convert it into the so-called either it's a graph or it's a language we can read, right? So you need a computer system to record all this information. And also nowadays we need a software. And usually scientists already develop a software with the particular very specific algorithms that can help you to do those so-called calculations, to help you to do the calculation. Yeah, but my time when I was during my college time, when we hands-on this, it's not that fully automatic. It's many components we need to do manually. Sometimes this column, we need to prepare the column ourselves, but it was quite fun. And then the results come out, those kind of like the printer, it's not that time don't have this full computer system, or the time the cost is too high, right? The cost is too high, so it's not affordable for the student training. So when you get a result, you get a simple kind of printer to print the result, print a chromatogram. I'll introduce you another concept, important concept called chromatogram is the result. Then we need to use the graph paper to draw the graph and work out. A lot of things need to work out and do the calculation manually. But luckily with the advancement of technology nowadays, you have a lot of helpers. The instrumentation, the computer, the software, then you just need to sit in front of the computer and do give your instruction, and then you can do the data analysis and get the results, and then you can analyze the data and then give the conclusion and give your comments. Right? Okay, come back to this the underlying principle of the technology is so-called chromatography. And these 3 weeks, we focus on gas chromatography. So in gas chromatography, basically the sample need to be introduced into the system for the product analysis or sample analysis. How to introduce in? So it's basically injected, and then because gas chromatography, so we know the mobile phase is a gas. So the molecule introduced in, later on, you need to find a way to vaporize those molecules into gaseous phase. Then it can be mixed, it can be carried by the gas as a mobile phase, as a carrier. then to go through the column. Just now before the class, I overheard some of you sounds like you were discussing on cars, automobile. So you can imagine that in GC, gas chromatography, the mobile phase actually also function as a BMW. BMW now is passing through this column, and then those sample molecules, they are passengers. You get me? But because this vehicle, this carrier is a gas, how the passengers can come on board?
They also yes.
Yes, you need to find a way to convert them to gas first. So that's why it's very simple. For this technology, if you want to consider, although I mentioned in the first place, I mentioned it's very powerful, but there's a condition. When you consider to apply this technology, then you need to think about the product you going to study, or the molecules, okay, chemicals you're going to study. Can you do this very first step or not? Means, is it easy for you, or is it cost effective for you to convert these chemicals into gaseous phase? There's another term, it's called, can you easily vaporize those things? If yes, then most likely, you can straight away consider this technique. Once you can vaporize them, then you supply the gas, right? You pump in the mobile phase, the gas, then gas will bring all these molecules, go through whatever tube, also you call it column. Right, that's right. So that's why we need a gadget, we need a device for us to do it. So later on, engineer, they design, they combine all these considerations, they put them together, then they design a component, it's called injector. So you use a needle, use a syringe to inject. So if we understand this, then we can consider a lot of stuff, then we can study. If the original product is a cheesecake, can you consider this possible, right? Then you need to look at which particular guy or analyte you're going to study. Then you look at this. If that guy or that chemical, you can vaporize them, although original is inside a cheesecake, is a solid, but it's okay. Usually what we do is we convert whatever into liquid format. You convert first, because it's quite hard to imagine. Just now I show you the instrumentation diagram. Usually it is quite hard to imagine that you throw a stone inside the column. Then how to vaporize, right? You throw a solid directly into the tube. Then how to vaporize? Much harder. So usually what we do is we convert it into liquid, a solution first. Then we introduce the solution into the injector, and then in the injector, let me ask you, this one you are kind of expert already, you're quite familiar. Let me ask you, because the requirements, you need to vaporize them. So when you are the chemical engineer, you need to design this, you need to design a device. What will be the thinking behind? What? You design a component, maybe enclosed, then when this thing comes in, what are you going to apply? Exactly. You heat it up, then where is it vaporized? Then you force the gas mobile phase coming, then you will naturally bring the molecules into the column. Exactly, that was the design behind. So that's why they designed the injector. So injector, that's why there's a heating element, there's a temperature control, all this so on and so forth. But after that, the important part, when the molecule has been vaporized, and then now carried by the BMW, which is the mobile phase for the particular analysis, then all of them, they go into the column, right? Now the important thing happened, right? So the different molecules, then they partition between the stationary phase and the mobile phase. And then the logic, also called the principle, is also quite straightforward. Then separation happens. Why is that so? Because the separation now is based on the unique affinity of each molecules for that particular stationary phase. Right? For instance, two of us, we come into this room. Let's say from time to time we touch the wall. If I like this wall very much, or whatever, vice versa, the wall, that means the stationary phase likes me very much. So the stationary phase will hold me very tightly. So what is the consequences? As the name suggests, stationary, because it's the wall, cannot move. If she likes me very much, she will hold me and I cannot move. So that's why in this column, then I'm still traveling, but I'm traveling at a much lower speed. In the contrary, he does not like the stationary phase. That stationary phase, in a way, holds him, has a weaker impact. So the stationary cannot hold him back. Then he will, don't forget, always there's a constant supply of the mobile phase and pushing all the molecules through the column, right? So the guy, another molecule doesn't like the stationary phase. That means the affinity of that molecule for that stationary phase is low. Then you naturally be pushed out from the column in a very fast manner. So it's because of this. It's because this different interaction between the different molecules with the stationary phase and a fixed stationary phase. Then their traveling speeds, the traveling rates in this so-called tunnel or so-called column are different. Then, right, when they move along this journey, they are separated. Simple as that. Okay? So don't worry, we'll come back to this point. We'll reiterate until you kind of get the so-called picture and sort of understand. So a few keywords. Sample, you need to do a bit of treatment, and key thing is you need to be able to vaporize it. Then in another word, next time in a quiz, I give you a question, I give you a molecule, even I give you a structure of a molecule. Then I ask you whether you can apply the technique. And then very straightforward, you just recall the fundamental so-called chemical and physical property of it. If it's very hard for you to vaporize it, then you straight away forget about this technique, right? Then in that case, let me ask you further. How do I know whether I can vaporize this particular chemical or not?
Boiling point.
Okay, very good. He's very sharp. Every time he hit the point. Yes, the physical property directly associated with this nature is the boiling point. If the compound with very high boiling point, of course, it's very hard. So maybe for those compounds you forget about this technique. Then another two keyword is there are two phases. Always remember there are two phases here. Then the partition of these different chemicals. In particular, your target compounds. The compounds you're going to study, you're going to research, are very important. The partition of these different chemicals in the two phases. Partition. And partition, there's another word to describe, is the affinity of that chemical for the fixed stationary phase. Alright, so let's move on. So that's another so-called simplified schematic diagram to describe to you how the different molecules are separated in the GC column. So you see, first of all, molecules, they are mixed together, and after that they are carried by the gas, the mobile phase. And mobile phase, you see, from left to right, they force the different molecules force them out from the column. But along the way, everybody, they have a chance to interact with. You can see these two lines highlighted in yellow that represent the stationary phase. You can visualize this manner. This stationary phase is another special chemical. It's another special chemical. The one probably easy, it's easier for you to kind of visualize. So it's another chemical, or it's another particular very special type of chemical solvent. Then all these individual molecules, when they interact with this solvent, there will be interactions. And then the so-called solubility, we can use different terms to describe it. For a particular molecule, the solubility of that molecule in this particular solvent, in this case the solvent fixed already, no? The solubility is different from the other molecule, or you can call it affinity, or you can call it the partition rate, partition rate of that particular molecule in this particular solvent, which is called molecular. If the affinity is high, then it will kind of dissolve in this stationary phase. Dissolve in this stationary means it's stuck there, it cannot move. Then the other people, in particular this case, the guy in blue color, then they move faster, because all of them, they are constantly pushed by the mobile phase. The mobile phase comes in at a constant flow rate, right? So that's why in this case, the guy in red color, they have a strong interaction with the stationary phase. Means they dissolve more in the stationary phase. So that's why they stay back. They stay back more and more and more. Then these different molecules, they are separated. I hope so far it's quite clear, right? It's still quite straightforward, right? So the principle is not that complex or not that difficult to understand, right? Good. So far, any things you want to further clarify? No, No, Okay. Then I give you questions. Right? I give you questions and see whether you really understand. Okay. Pop quiz. So far, based on what we have discussed, based on understanding, so can any one of you quickly share with me? Question number 1.
They are different solubility. That's why with the highest solubility, they will be separated first.
Okay, good, very good. Something like that. Because this one is just a quick.
Every component is solubility.
Okay, good. You are more specific now. Because now it's based on our previous discussion. It's a very quick assessment. So you can describe in general, right? Because different chemical compounds or different molecules, right? They have different interactions with stationary phase, right? So that's why when they move along the column, when they move through the column, so the different interaction will result in the different traveling speed of the different molecule, and it results the separation of the different molecules. Okay, so that's the idea, So actually, it's quite straightforward. So second question, share with me one key property that makes the compounds suitable for GC analysis. Yes, exactly. The compound need to be able to be vaporized, and you look at the boiling point. Okay, very good. All of you pay attention to our discussion, and I can see you understand quite well. Very good. All right, I think next about less than 10 minutes, I'll quickly go through the operating principle again. Basically, all this we discussed before, because the molecules, right? Because of the so-called different interaction with the stationary phase, they elute. They elute. Elute is another kind of a more academic term. It basically means they travel, they travel through the column. They travel at different rates, they induce at different rates. Then those chemicals or those molecules, they favor the stationary phase. That means they like the stationary phase more, then they will have longer retention time. This one also quite straightforward, right? We explained before. If they like the stationary phase, they will be hold back. So those molecules, they favor the mobile phase. That means they will stay in the mobile phase longer time. But the direct consequence, if they always stay inside the mobile phase, then the direct consequence, because the mobile phase is always in the move, so that's why they travel very fast. Right? They travel very fast. So they are going to come out from this column first. Right? So this is a repeat. So as discussed, we need a data, we need a detector, we need a computer system to record all the signal, all the data, and then do the calculation. So this one, which some of you share, you can use another term in terms of the so-called affinity, or another time is the relative solubility. You look at different molecules, their solubility in that particular stationary phase. If solubility is relatively high in a liquid stationary phase, then of course it results into longer retention time. Right. Then I'm going to introduce you another technical term, and this one you need to remember. Just now we say the technique is called language, or the term is called chromatography. Then the result, actually we call the result, is present in this format. This presentation, we call it chromatogram. What is chromatogram? By definition, is a plot of the detected signal as a function of time. So you can visualize the x-axis actually is the elapsed time, right? It's the traveling time. Then the y-axis is the, let's say, imagine there's an eye, is the instrument detector, is the signal it can detect. Right? It consists of peak of each individual molecule, right? And then the area under that particular peak represent the amount of the chemical is inside the column. So that area is related to the amount, right? Related to the quantity, right? And then the retention time. Okay, there are two technical terms here. Let me see. One or two. Yes, two. One is called chromatogram. Chromatogram overall is the result of this technique. Then you need to remember, you need to understand the other term is the so-called retention time. Capital R, retention time. This retention time is the time for a particular molecule to travel through the column. Means from the time it was injected into the column till the time it came out from the column. So this elapsed time is called retention time for that particular molecule, or for that particular chemical compound. To be more specific, okay, I show you another diagram. In the this is called chromatogram. You can see the y-axis actually is a detector signal. The detector will detect the signal and pass this information to the computer. The software actually will record the information, and nowadays the computer plus the software, right, it will help you to actually plot this graph. And this graph, for this technique, we use the very scientific name, we call it chromatogram. So that's why you can see the y-axis actually is the detected signal. It's those electronic signals, how intense it is, right? This one may be very small, but the other one is very, very intense. So the hardware, the detector record these electronic signals and then record it. So the y-axis is the detected signal. So you can see the first guy is the small guy. It's not that the signal is not as strong. But the second guy is a very fat, very big boy. Right, so you see, but you look at the second one is more obvious. So this signal is a Gaussian, it follows a Gaussian distribution. So you can see here, usually you look at here, we look at the peak, the peak maximum. From the peak maximum, you draw a horizontal line, also called the vertical line to the y-axis. So the origin point is the time you introduce this compound into the column. Then it travels until here. When you see the peak maximum, we define this travel time as the retention time for this particular molecule. Right? Is that clear enough? So it's the TR for compound B. Then for this small guy there, then the retention time for compound A is different from the traveling time or so-called retention for compound B. So the retention time for B is much shorter. So it's TR. T means time. This way is sometimes we use a capital, sometimes it's a small capital R. It doesn't matter. But basically R means retention time. And for that particular compound, it's called compound A. So then in terms of value, you can visualize that TRA is very small, and TRB is much longer, much bigger, right? So means in this particular experiment, compound A is the compound, okay, runs very fast in the column, so it is eluted from the system or from the instrument first. So all these are the so-called fun. So today the first lecture we introduce you the fundamental technical terms and concepts and principles first. So I reiterate. So the retention time is the time for that particular chemical or so-called molecule for this molecule to travel through the column. But you need to look at the peak maximum, okay, in the detector signal. Then this peak, you have an ideal case. For each molecule, for each compound, you will get a nice Gaussian distribution. Then the area under this particular peak represent the amount of chemical inside. So very obviously, from this direct result, you can see that, you can straightaway guess that, for this experiment, actually the product we study, it contains a lot of this compound B, and relatively just tiny bit of this compound A, right? And this is the basis for our further quantification. And indeed, for this very powerful technique, at the end of the day, in many cases, our end objective is we need to look at the quantification of those so-called chemicals we're going to study. But then quantification, a lot of things come in. So those things we have learned, right? Then is in the generic approach, generic technique. For instance, you need to do quantification like what we did in our UV-Vis technique. We either consider a standard curve method to do the quantification or standard addition method to quantify. Then we need a pure, let's say we study compound B, then we need to the pure crystal compound B as a reference for us to do the quantification, right? So we'll elaborate this later on. Okay, to close, sorry again. W. Okay, W is the width of that peak. Okay, so that one is not that important. Usually we don't look at it because this one can be used as an indicator, also called a proxy, right? To represent the amount of the particular chemical or molecule. But our experience, practical experience because the bandwidth, also called the peak width, is relatively not as accurate as because you use the entire area under the particular area. The information is richer. That means it will give you more precise, more accurate results. Okay, very good question. Very sharp, guys. Okay, before we close, before we give you the final pause questions, I probably give you I show you a very small video clip to help you to understand the chromatography and in particular the gas chromatography separation. It's because of the different interaction, right? So those green guys, they stay more in the stationary phase. So that's why they move very slow. So the red guy comes up, you see, the red signal comes up. You see, that's how different molecules are separated. Okay, last minute, last 2 minutes, I quickly, I think now it should be clear enough. Okay, last 2 questions, very quickly. Please define the compound's mutation time.
The duration of it is the journey.
Okay, for any given chemical, what determines the retention time?
Affinity towards the stationary phase.
Exactly. Okay. Thank you for your collaboration. I think you pay full attention. You understand very well for this topic. Okay, I'll see you next